Ciaran Lee, who's going to tell us about computation in GPTs.
Thanks very much, Matt. Okay, so this talk is based on a paper of the same name. The archive reference is there if anybody's interested, and it's joint work with John Barrett. Okay, so quantum theory appears to offer dramatic new advantages for information processing tasks. And this kind of raises the question of what broad relationships exist between physical principles and information theoretic advantages. And many people much progress has already been made in kind of understanding the connections between physical principles and some information processing tasks, such as cryptography and communication complexity problems. And this has led to insights that has resulted in device-independent cryptography, among other things. So while these questions appear to have foundational interest, they also, have practical implications. So, despite this, relatively little has been learned about the connections between physical principles and computation. And most previous investigations into computation beyond the usual quantum formalism have kind of focused around non-standard modifications of quantum theory. And these often come with immense computational power and entail unphysical consequences. So for example, closed time-like curves can solve NP-complete problems, and so can nonlinear quantum theory. So in contrast to that, today we're going to look at computation in the framework of operational probabilistic theories that have been talked about by Carlo, Maria and Howard before. So here we're going to kind of take Carlo's point of view. So an operational theory is going to specify some set of laboratory devices that we can connect together in different ways and then assign a probability to the different possible outcomes. Okay, so I'm now going to give you a brief outline of the structure of the rest of the talk. So I'm going to first start off by introducing the specific problem that I'm going to talk about today. Then I'm going to, in a slightly more rigorous fashion, introduce the framework for operational theories that will help us kind of make this question rigorous. And then I'm going to discuss some of our results. Okay, so the class of problems that are efficiently solvable by a quantum computer is usually denoted by VQP. And many people are kind of interested in what a quantum computer can and can't do in principle, which is another way of saying is how big can this class be? And people have known for about 15 years that the best upper bound on this class is given by this thing here. So AWPP here is just some classical complexity class. Its definition isn't important for the purposes of this talk. Just know that this is the best known upper bound for this class. And PP and P-space here are the more well-known things that people might know. So here's the definitions again. Again, they're not important, just if you want to remind yourself. So for example, P-space contains all problems that can be solved by a classical computer using only a polynomial amount of memory. Okay, so the problem that we're going to discuss today is this. So what's the minimal set of physical principles such that efficient computation in an operational theory satisfies this inclusion? So by the inclusion I mean this thing here. So as it stands, this question isn't well posed because, well, first of all, I haven't defined what an operational theory is, but moreover, I haven't defined what efficient computation in some operational theory is. So in order to do that, I'm going to have to introduce the framework for operational theories that Carlo also talked about. So today we're going to work in the circuit framework that's been developed by Lucian Hardy and members from the group Pavia. So in this theory, the kind of primitive notions are these things called tests. And tests represent one use of a physical device. So a physical device can be thought of as having some input ports, some output ports, and having a classical pointer on top, such that when this physical device is used, this classical pointer ends up in one of a number of different positions, and this signifies some event that's occurred. So we can think of tests as some collection of events. So we could write that algebraically like this, with the i's here index the kind of set of possible pointer positions, and the e sub I are the possible events that could occur. Okay, so we can also think of physical systems as passing between these input and output ports of these tests, and these kind of come in different types. So they're labeled by A, B, C, something like this. So the nice thing about this framework is it allows us to diagrammatically represent what we mean by a test. So here's a circuit that represents a test from some input port of type A, some output port of type B, and I here label the possible classical pointer positions. So when we use that test in some experiment, the classical pointer ends up in one of the number of positions I, and then we can also draw circuits like this that represent that kind of situation. And tests with no input ports can be said to prepare a system. Some quantum theories are preparing some density matrix. Tests with no output measure a system. So you can think of this as some sort of POV element if you want in quantum theory. We can also compose tests sequentially. So if the output port of the first test has the same type as the input port of the second test, we can compose them in sequence. We can also compose things in parallel, like so. So in an operational theory, we can draw kind of circuits that represent the connections of different physical devices in some experiment. And we can also draw diagrams that represent the specific events or the outcomes in that experiment. Okay, so this is all nice. We have this kind of circuit structure going on. But another fundamental kind of requirement on the physical theory is that it should be able to give probabilistic predictions about the occurrences of certain outcomes. So we need some sort of probabilistic structure. So we're going to demand that closed circuits correspond to probabilities like this. And this is quite nice, this kind of probabilistic structure, because it implies a linear structure. So for example, here's the closed circuit we had a few slides back, and now this corresponds to some joint probability distribution. And we can use that fact to show that this preparation here corresponds to some vector, this measurement corresponds to another vector, and then this test applied in the middle corresponds to some matrix. And moreover, the way in which we calculate this probability can be shown to be just by taking the inner product between these things. Okay, so we can kind of think of tests or transformations from some system A to some system B as inducing a linear map between the corresponding vectors. So here we kind of have this test here, and we could see that it kind of it induces some linear map between this vector space and the outcome vector space here. And so once we fix a basis for those vector spaces, this transformation will have a matrix representation, which is what's going on here. But you should note that this thing is we have this single system transformation here applied in parallel with doing nothing here, the identity transformation. And so we had a big matrix representing that whole composite process. But in general, there might be no way to relate the matrix of this big composite thing to the matrix of this individual thing when acting just on this system alone. So this is another way of saying it. So if some transformation from some system A to some system B acts on one half of some joint system, there may be no simple way to relate the linear map acting on this joint system to the action of the transformation when it's applied only to system A. So in order to have a nice way to kind of link these two things, we introduced this following principle called tomographic locality. So a theory is going to satisfy tomographic locality if every transformation can be fully characterized by local process tomography, which means that if this is a transformation or test in my theory, I can fully characterize it by putting in product preparations and performing product measurements on the output. And this gives us a really nice way to kind of relate the matrices of transformations applied in parallel. So here is the circuit we saw a few slides ago, and we saw that the probability was calculated by taking this inner product, where M was the matrix corresponding to this composite transformation here. But now, given tomographic locality, one can prove that that matrix is actually the tensor product, the vector space tensor product, of the matrix corresponding to this transformation when applied from A to B on its own, and the identity matrix on this system. So that gives us a nice way to link these two things. Okay. And from now on, we're going to assume that tomographic locality is satisfied. Okay, so another nice feature of this kind of Hardy-Pavia framework is that a notion of causality isn't implicit, and one can actually articulate precisely what it means for a theory to be causal. And moreover, one can talk about theories that don't satisfy this notion of causality, which is quite nice. So as Colin Marie was discussing, an operational theory will be said to be causal. The probability of a preparation is independent of the choice of measurement that follows the preparation. And here's an algebraic way of writing that, but I'm not going to get into that now. So one can think of this kind of causality principle as a way of kind of formalizing what it means to disallow signaling from the future. But despite this, there's nothing obviously pathological about theories without this notion of causality. I mean, there's nothing in the framework, as it's stated, that kind of compels us to interpret circuits as some sequence of tests applied in some temporal order, such that this temporal order matches the order of composition in our circuits. So from now on, we're not going to assume all our theories are causal. Okay, so we've seen that we can draw circuits that represent the experimental setups and specific events that took place in certain runs of that experiment. But what else do we need to kind of consider these circuits as some sort of model of computation? What we're going to need to find is a uniform circuit family of circuits in this operational theory. Okay, so going back to the usual classical and quantum case, a circuit model is indexed by some positive integer n, and this integer n corresponds to the size of the input to the circuit. So the usual way we interpret this thing is we have some state that encodes the problem we want to solve. We input this into one of our circuits, run the computation, perform our measurement, and then the result of that measurement tells us the answer to our computation. And each circuit will be built with some polynomial number of gates, and we can efficiently kind of classically describe these circuits, which means that we can't, in some sense, hard to solve problems in the way in which we compose these gates. Okay, so in a generalized kind of circuit model, the ones that come from these operational theories we've been discussing, I've said that we haven't assumed a notion of causality, right? So these circuits, in some sense, don't have a preferred direction. So there's nothing really that compels us to interpret them as some set of gates acting on some input. So what we're going to do now is, instead of letting the size of the input state index our circuit family, we're going to let the actual circuit, the classical string x, do it. So we're going to let the entire circuit, in some sense, encode our problem. And that's why we have this x with the classical string here. And while it mightn't be the case that in a specific theory there'll be some sort of universal gate set for computation, we're going to demand that each circuit will be built from some polynomial number of gates from some finite gate set. We need two more conditions in order to talk about uniformity here. One is the following. So given some matrix representing the outcome of a particular gate in our circuit, we saw that we could represent these by matrices, we demand that we can efficiently approximate the entries of these matrices. And this kind of has some physical connotation, which is that if we're in our lab and we have some sort of devices, we can never perfectly employ or align them, so there'll be some error there. And this is kind of captured in this thing. And also, we demand that we can classically describe this thing efficiently, so that we can't encode hard problems in that way. Okay, so we need to now talk about an acceptance criterion, because we talked about our uniformity principle. So in quantum computation, all gates are deterministic, and without loss of generality, we can postpone all measurements to the end of computation. And we'll say a quantum circuit accepts some input state if the measurement of the first outcome qubit is 0. But in an arbitrary theory, this need not be the case. I mean, without loss of generality, we mightn't be able to postpone measurements to the end. So we're going to need a more general acceptance criterion. So, okay, so a way in which one might try to solve a computational problem with a GPT is, if you're given the problem instance, which would be the classical string x, you go away and construct C of x, which is your circuit, so it could look something like this. Then you run your circuit, you press the big go button, and all the classical pointers end up in their final position, and then you can read off the outcomes associated with each gate. And so what we need is a way to partition this outcome set into an accepting and a rejecting subset. Okay, so the way in which we do that is we have some function, a, such that when you give it a possible circuit outcome, it'll give you 0 or 1 for accept or reject. And we're going to demand that this function is also efficiently computable, because we don't want the way in which we partition these outcome sets to encode a hard problem. Okay, so now that we have a uniformity principle, an acceptance criterion, we can define what efficient computation is in an arbitrary theory. So this is, and then the probability to accept is just we sum over all accepting outcomes like this. Okay, so we can define this class BGP for specific theory G. So for an operational theory G, a language is in this class if there exists a poly-sized uniform family of circuits and an efficient acceptance criterion such that if X is in the language, then we accept a probability at least 2/3, etc. So this is like the usual definition of BQP, but now we have it for a G. And these kind of constants are irrelevant. We can do amplification on them in the usual way. Okay, so now that we've kind of defined efficient computation in these theories, we can go back and answer the question I posed at the start at the top. So we have it here. So okay, so this is one of our results, which says that for any operational theory G satisfying only tomographic locality, we have the following inclusion here, which is the same as the best known quantum inclusion. I just want to kind of briefly sketch how the role of the assumptions that went into constructing our theory and also tomographic locality, how they kind of come into play in the proof. So the kind of linear structure, the fact that the joint probability for a circuit can be written as some inner product over some matrices, that plays a big role. And as we saw, that arises from the ability for our theory to kind of give probabilistic predictions about the occurrences of certain events. So that's a kind of very basic kind of assumption of what a physical theory should do, so it's not really a big thing in proving the theorem. And we also need tomographic locality. And the reason that comes into it is that we know that when we build our circuit from gates from this uniform gate set, the matrix representation of these gates have efficiently computable entries. But now when we compose two of these gates in parallel, there's no reason that the matrix corresponding to that parallel composition will have efficiently computable entries. But as we saw, when we assumed homographic locality, it's a way in which to associate this big composite matrix to the individual matrices of the gates that were composed, and so that's what we need that for. Okay, so the best upper bounds on this quantum class follow from very mild assumptions. So we'd like to it would be nice if we could actually do better. Because I mean, we don't even assume a notion of causality in the proof, so it feels like there's no unique quantum stuff that goes into that proof. So some other questions we can ask now that we have this framework in place. One is, can quantum theory simulate computation in any of these operational theories? If so, this could potentially provide an explanation of the quantum speedup. But in more general, are there certain situations in which quantum theory is provably optimal for computation? And there is one that we found so far, and I'll discuss it now. So Scott Aronson introduced this notion of post-selected quantum computer, which is essentially quantum circuits with a post-selected register. We only consider those runs of the computation for which a measurement of the post-selected register qubit yields 0, and all other runs of the experiment that don't end up in this position are discarded. So in some sense we can compress maybe an exponential number of time down to one computational step. So Aronson proved that this class, post-BQP, is equal to this class PP. It's a nice proof. But from our point of view, this is quite interesting, right? Because we know that efficient computation in all theories is in this thing. It's in this class PP. So essentially, a quantum computer with post-selection can simulate computation in any generalized probabilistic theory. But actually, we can say a little bit more. We can define generalized circuits with post-selection. In this case, we can post-select on some subset of possible circuit outcomes, as long as you know it's efficiently computable in some sense. And then one can prove this theorem. So for any tomographically local theory, we have the following. So post-BGP, so G stands for a specific theory that satisfies tomographic locality. We have that this is contained in post-BQP, which is the quantum case. So the way to sum this theorem up is, in a world with post-selection, quantum theory is optimal for computation in the space of all these tomographically local operational theories, which is quite nice. Okay, so in conclusion, we've kind of defined the class of problems that can be efficiently solved by an arbitrary operational probabilistic theory, and then we've shown that theories satisfying tomographic locality satisfy the best known quantum bounds on this class. And we've also shown that in the world with post-selection, quantum theory is optimal for computation in this whole space. Okay, so some kind of nice questions we could ask now. We haven't assumed a principle of causality, but in some sense our circuits, the gates in our circuits still appear in some fixed structure. So it'd be nice to kind of see what we could do in the case where there was no fixed structure between these gates, in the case of kind of indefinite causal structure. That would be kind of nice. And moreover, because there's so much freedom in constructing these operational theories, can we construct one that can simulate quantum computation? So if so, then we could compare quantum theory to this other theory in the hope of learning why quantum theory isn't that way. Maybe something bad happens in that theory, it's pathological in some way, and in studying it we can learn more about quantum theory. Okay, thanks very much.
We have quite a bit of time for questions.
Ciaran, you have various conditions in your definition of computation, or the usual kind of no cheating conditions.
Say it again.
The usual kind of no cheating conditions, right? You don't want
I didn't catch that one.
encode
Oh yeah, exactly. Yeah.
But I was wondering if, because you're almost everywhere forcing everything to be efficiently describable, whether that in itself excludes some generalized theories.
Yeah, so it seems like that might be the case, but I don't think so, because we make those definitions in quantum theory as well. So you can actually have you can come up with unitary transformations in quantum theory that do encode hard problems, but you'd kind of expect to never see them in the lab. So those assumptions do go into the definition of BQP as well. So I don't think we're assuming a lot extra here if we're assuming these things for quantum theory. Because even in classical theory, you could have situations where you could flip a coin and the binary expansion of the probability of getting heads could encode a hard problem. But you'd never expect that to actually happen in the lab, right? If I could find a coin that's weighted in such a way that when I do it and kind of build up the distribution, I could solve a hard problem. So we even make those assumptions in classical theory, and without them you can actually get really pathological things going on even in classical theory. So I don't think we're assuming too much in saying those things. We're just assuring that those pathological things don't happen.
I had in mind some stuff of Lucian from years ago when states seem to be always exponentially large. Every state has exponential information. Maybe that's...
Yeah, I'm not sure. So Lucian did have a paper on kind of quantum gravity computers. Was that something to do with that, or? yeah, I don't think these assumptions are too strong because we make them in classical and quantum theory as well. So.
Any other questions?
I just had a quick question, possibly this was something that you said and I missed. Going back to Scott Harrison's result and your corollary, you said that anything that is solvable, recognizable by generalized probabilistic theories is a PP. Is that requiring local topography? Or
Yes, yeah, yeah. So yeah, in the statement of the theorem we had.
Okay, so
Yeah.
so
Yeah, so we're kind of always assuming tomography locality in some sense. Yeah.
even for that part.
Yeah.
So maybe relatedly, if you could sort of put some limits on how bad tomographic non-locality could be in terms of how hard it is to compute the transformations applied to parallel.
Yeah.
Presumably you could say something about some tomographically non-local theory.
Yeah, absolutely. So kind of in the, I won't go back to it now, but in the proof of this, you don't need the full tomographic locality principle, just, the fact that when we combine two transformations, the matrix that results for that composite transformation is in some sense easily describable from the matrices of the individual transformations. So, for example, real quantum theory satisfies that, and so would form part of this theorem. So yeah, it'd be nice to kind of find the weakened tomographic principle that kind of like exactly captures this notion. That would be kind of nice to find. But yeah, it'd be nice to kind of even like n local or something like that. We could see what computation happened there, and if there was a way to kind of efficiently describe these things.
Was the computational power also classical?
It's so the way people, it's called, this is class called BPP sub path, and people don't know exactly what the computational power of it is, but they've shown, as nearly all things in complexity theory, if BPP path is equal to PP or post BPP, then the polynomial hierarchy collapses to the third level. So it's believed to be a strict subclass of this, but it's unknown. It's definitely in here, but people don't know if it's strict or not.
So I think Scott also has some other results which are sort of similar to this, looking at closed timeline curves and causality. You said you haven't got causality in your framework.
Yeah. So
is that something you've?
So yeah, it is. There are some subtleties there between having kind of. So when I write post BQP here, it's some sort of model of computation where you impose this post selection on the model of computation. Whereas now, if you have some sort of well-defined generalized probabilistic theory that's not causal, you might think in some sense maybe there's some notion of post selection in that theory. So looking at kind of efficient computation there, I'm not sure that would be the efficient computation in a theory with post selection would be equal to kind of this model of computation. So there's some subtlety is what's going on there.
But I guess your theories must exclude these
exactly
time-like curve non-linearities that are excluded.
Yeah, exactly, because in some sense this kind of closed time-like curves induces a non-linear transformation, so they wouldn't be allowed in this framework. But
is it local tomography that contradicts?
I'm not sure. I think it's just the fact that these kind of closed time-like curves are non-linear transformations in and of themselves. They also violate our uniformity principle, because in some sense the way in which they have it is they have some sort of box with some loop going like this, but this loop is some sort of fixed solution that comes with the box. So here's the box and it's already programmed with the ability to do this loop. So finding that loop in the first place is very computation tricky. So that's where the computational power comes from, the ability that they've in some sense stored that computation in this box already. So that would violate the uniformity principle, but I think also that transformation is non-linear and so wouldn't be allowed in this kind of framework. But there is some subtlety going on there that I'm not fully clear on yet. Yeah.
Have you looked into the possibility of computing uncomputable problems, like the halting problem?
Well, no. So I guess the halting problem is uncomputable, and we're kind of looking at efficient computation, these frameworks, and because we kind of have this theorem here, we know that they're contained in these things, which are things that the halting problem definitely isn't in. So yeah. So but it'd be interesting to look at kind of computation and not in the kind of efficient regime. So kind of we're looking here at bounded error computation. It'd be interesting to look at exact computation. That might be interesting too, but we haven't done it yet.
Okay, we should move on to the next talk, so let's thank Ciaran again.